And so what I want to talk about now is a more, the discussion in the previous lecture was basically based on the fact that there are some fluid mechanic effects that we can account for by a simple theory where the flame speed is just constant. And we have seen that it explains a variety of things, but not maybe all. So now we want to expand on that, and elaborate on this. And the discussion is based on a multi-scale analysis, which I sort of alluded to before, namely that we have two scales, the flame thickness and the large hydrodynamic scale, and we are assuming that delta is much smaller than 1, but also we are assuming that the activation energy parameter is much smaller than delta, which means that the reaction zone is a thin region embedded within the flame zone, which itself is thin compared to the hydrodynamic zone. So you see the complexity, and that's why maybe the words multi-scale. And now some references. I'm going to skip that. The idea, again, I mentioned it a little earlier before, that we have a flame zone, and there is a reaction zone embedded in it. And in the limit, when delta goes to 0, it is a surface, and the surface is described by this function. And what we are interested is to determine essentially what is that surface and how it propagates, which is equivalent to determining the propagation speed or the flame speed. I showed that before, but it's a little more general now. So what we need is to find from inside the flame zone an expression for the flame speed or the burning rate. That is what I told you earlier, that's not known in general. So we will be able to obtain such a relation, but under thin flames under these conditions, okay? So the idea is that when you do, and I'm not showing the analysis, it's just the result, what it shows that, again, you have the Euler equation, but now viscous effects are weak. And so the yellow part is the new addition, which is the small effect due to viscous effect. The density remain to be piecewise constant, unburned and burned value across the surface F. And then the Rankine-Hugoniot relation will also have corrections due to the flame thickness, which are interpreted. I didn't write them in detail. You can find that in literature if interested. Essentially, since the flame has some thickness, as you see here, then not as originally the Rankine-Hugoniot relation tells you that the mass flux in is the mass flux out, because inside this control volume, some mass can accumulate and some can be transported sidewise, okay? And so those are the effect of these terms. They turn out to be relatively small, but anyway, they come from the analysis. And finally, the detail of the analysis give you an equation for the flame speed, which is to leading order the laminar flame speed, everything that we discussed in the previous lecture, and a correction term here. So all the yellow parts are the correction due to finite thickness of the flame. Finite but small, okay? And I will explain those terms in detail soon. K is, again, the flame stretch, as we have seen in the simple example. L is a coefficient that turn out that depend on the mixture properties and is known as the Markstein length in tribute to Markstein, who was the first to introduce the idea of curvature dependence, and so this is where it comes from. Something about the flame speed relation, some comments. So those are the two quantities that I already told you about. But note that unlike the assumption of Markstein, it depends on flame stretch, which means not only curvature, but more than curvature, okay? And the second thing is there is no phenomenological parameter here. There is a clear definition of L, which is going to come soon. And the same comment I made before, that if you know the flame speed, you have an evolution equation for the flame surface. But of course, that evolution equation is more complicated because it depends on K. K depends on the flow field. And so you have a coupled problem here between the flame and the flow. So you have to solve everything coupled, okay? Good, so first of all, flame stretch. Same definition as before. Flame stretch is the fractional area change of a Lagrangian surface element, meaning on the surface, that is retained on the surface. It's really a kinematic concept. And it's defined as 1 over A dA dt, where A is the small element of the flame surface. So at time t is the green part, at time t plus delta t. This delta is not the small parameter before. It meant a small change in time. It is the yellow part. And then you compute area from geometrical consideration of this just general curved surface. You compute it at a different time, take the limit when you go to 0, and this is the expression that you get. So it related to curvature, kappa is curvature, multiplied by the propagation speed of the flame. So it's minus VF kappa. And another term here, which in general can be written as n dotted with the curl of V cross n, but that can easily interpreted as the surface gradient. Gradient S meaning the gradient along the surface. Now, a general surface, there will be a gradient not only in one direction, there are two directions. And Vs is the component of the velocity on the surface, okay? And this is the two expression. So the first one tells you that the surface dilatation due to the propagation, as in a spherical flame, right? And the second one tells you it's a surface extension of the flame due to the velocity gradient. The curvature, by the way, can be computed as the divergence of the normal. The minus, again, just because of my choice of the coordinate, can be positive or negative depending if the normal is up or down. And generally speaking is the sum of two, the inverse of a curvature is the radius of curvature. So it's typically R1 and R2. So for example, a sphere has only one Rn, R1 and R2 are the same because of the symmetry. In a cylinder, one of the radius of curvature is the radius, the other one is infinite. It's the direction is flat. And other surfaces have similarly other forms. So again, I emphasize here that flame stretch is, again, an asymptotic concept because it is determined on the flame surface unambiguously. But not only that, it also is uniquely defined because I can compute it on the unburned side, I can compute it on the burned side. The reason for this is because Vs, which is the tangential velocity, is continuous across the flame to leading order, and that provide a unique definition of stretch. If you don't do that, then you can compute stretch at different location inside the flame, and it will give you different values, and whether this relation will hold or not, it's questionable. In fact, that have created some confusion in the literature. Okay. An example is the spherical flame. We have seen before how we computed it directly by the area and so on, but from this formula, it's very simple. The flow is radial, so this term is gone. It only comes from here. V sub f is r dot, and kappa is 2 over r. So you get this expression like before. For a stagnation point flow, the curvature is 0, the flame is flat, and the only contribution comes from the tangential gradient, which in this case is dV/dr, and that was computed before. V is epsilon r, and so you get the 2 epsilon, okay? This is the gradient because it's in cylindrical coordinates, right? In in planar form, in two-dimensional form, is just d by dx or d by dy. And then for a for a curved flame, for example, well, it depends on different segments. So for example, this segment where the curvature is negative, okay, because you see the normal point out and the radius of curvature of this segment is inward, so it has a negative curvature by this notation. And then the propagation speed is going to be negative because minus Vf times kappa, and the flame is pointing inward like that, whereas in this segment where kappa is positive, the propagation, it expands, and so it's a positive, propagate positive. So flame segment concave are compressed, convex are stretched. Those are compressed, those are stretched. And it's similar to an outwardly and inwardly propagation. That's why we study these examples, because they illuminate on more complex geometry of this kind. But the second term comes from the strain or the flow field. And so you see if there is a gradient here, the arrows are a little smaller, so the gradient is negative. So this part is compressed, as opposed to the part here where the gradient points outward, it's stretched, okay? Of course, that depends on the local flow field. Okay, so just a quick comment here. If you take this expression and you use some vector identities and just manipulate it mathematically, you can rederive from it the following relation. Vf kappa remain the same, and this part can be expressed as V dot n kappa. That's the strain rate, which is defined here, and plus the divergence of V. Now, in the hydrodynamic theory, divergence of V is 0 because it's 0 on the unburned side, 0 on the burned side, and we computed at the flame. And this is the strain rate, and these two terms combine into the flame speed. And so one often can write stretch as the flame speed times kappa plus the strain rate. But note that this is true only in the hydrodynamic limit when the divergence of V equal to 0. When divergence V is not 0, and you choose a certain surface as your flame surface, numerically say, then divergence V is not 0 there, and so you are either overestimated the stretch rate or computing a stretch rate which is not necessarily consistent with this theory. Here is an example of a DNS, a direct numerical simulation of spherically expanding flame. Here is the profile of the temperature, the solid curve. Forget the dash curve. It's asymptotic result, but it doesn't matter. And the red curve is a divergence of V. Clearly, it will vanish on where the temperature is almost constant, the burn temperature, right? Because the density is constant there. And it will vanish also far to the right where the density is nearly the density of the unburned gases, right? Now, if you compute the stretch rate, okay, now it's a spherically expanding flame, so this term is out. But you have to be careful, because if you compute simply the strain rate and don't pay attention to this divergence, you're going to get a solution which is like the blue curve. The red curve is the divergence of V. Note that this is the extent of the flame, where the temperature changed from 1 to about 7, 1 to 7. So here and here, the stretch rate is constant, but if you compute it, including the divergence of the velocity, you're going to get something that varies from point to point. If, however, you choose to be consistent with the theory and eliminate that term, or just set it to 0, or however you do it, then you obtain those green circle, which show you it's a constant stretch as it should be. So you have to be careful again when you make choices which have some ambiguity. That's the point. Okay, here I am quickly showing that if you compute in the hydrodynamic limit the stretch by curvature and strain, you get exactly the same relation as before. Note, however, that strain is not 0, because strain is not only tangential strain. In spherical coordinates, there is also normal strain. And so, in fact, it turned out that the normal strain is this, and the curvature is here, and when you add the two, you get the stretch rate correctly. The same thing in the stagnation point flow. It comes directly from the strain rate, so that's simple. This is an example of a flame where you can compute the stretch rate if you know, say, the geometry. I assumed here that you have a cone, which is the geometry in 3 dimensions, and you see that the stretch depends on the angle alpha, and it's always negative. So this flame, the stretch is, the flame is totally compressed, okay? But don't forget that this doesn't capture correctly the tip, where you have a highly curved segment, and it affects, of course, the overall picture. Okay. Here is a steadily propagating cusp-like flame. How do we create them? We're going to see in the future. But what you have is the unburned gas, and you have here the flame in the hydrodynamic limit that I discussed. Is just that it was computed numerically, because we cannot do that analytically. And what you see here are the streamlines, and what you see in the flame is propagated to the left at a constant speed u, which is not the laminar flame speed. In fact, it's higher than the laminar flame speed. And due to expansion, the unburned gas I'm sorry, it's not seen so well, maybe because of the light, but I don't know. Anyway, you see that, now you can see a little bit better. You see the streamlines here in the unburned gas. Due to gas expansion, there is a motion in the unburned gas that tend to sort of support this cusp or cusp-like structure. And you see also that the velocity in the burned gas is like much higher than in the unburned gas, which is practically 0. This flame is propagated in a quiescent mixture. That's the way it was calculated. And you can compute the strain rate, the total stretch, the curvature of the flame. And okay, so we spoke about flame stretch. We saw the relation to flame speed. What about this Markstein length? So the Markstein length has an expression as such that was derived. Note that the Markstein length is the first thing, it's proportional to the flame thickness. So it's a quantity which is relatively small. It's of the same order as, because it originates from the flame, from the internal structure of the flame. Sigma is the expansion ratio. It's always bigger than 1, so this quantity is always positive. This integral, it's a simple integral to compute. It's a number, basically. And it's also positive, so it doesn't, it can be verified that it's positive. It has no consequence. But what you have here, it's a Lewis number, effective, I will define it soon, -1. So this term can be sometimes positive, sometimes negative, depending on the effective Lewis number. In other words, so it affects the Marx-Stein length. And in fact, when the Lewis number is sufficiently less than 1, the Marx-Stein length can be negative. Marx-Stein length is not a length, it's a coefficient that has a length, it's of a length scale. And so it can be negative. So Marx-Stein length can be negative for subunity Lewis number or sufficiently subunity and positive otherwise. The other parameters in here is just the Zeldovich number, which is defined here. And this expression is good for constant properties. I will just flash later the equation for non-constant properties. Now, what is the effective Lewis number? The effective Lewis number turned out from the derivation that it's a weighted average of the two Lewis numbers, that of the fuel and that of the oxidizer. In fact, it's heavily weighted towards the deficient one. So in a lean mixture, it's more heavily weighted with the Lewis number of the fuel. In a rich mixture, is more heavily weighted with respect to the oxidizer. Phi tilde is not exactly the equivalence ratio, but it's related. The equivalence ratio, it's a deviation of the equivalence ratio from 1. So it's always positive. In other words, it's for a lean mixture is 1 over phi minus 1, which is always a positive quantity. For a rich mixture, it's phi minus 1. You see, the equivalence ratio, it's a number that goes from 0 to infinity. So it's a sort of, it doesn't have a symmetry. And so when you define it this way, it has a more symmetry on the one side to another. But it's just a mathematical expression. Now, if you are at stoichiometry, which means phi tilde is 0, right? Phi is 1, then it's exactly the mean of the fuel and the oxidizer, right? LEF plus LEO divided by 2. Otherwise, the lean mixture count more. One more comment is that the Marx-Stein lengths can be also controlled by the pressure level, not only by the mixture properties and their Lewis number, but also by the pressure. Why? It is proportional to the flame thickness. So you increase the pressure, the flame thickness decreases, and it affects the Marx-Stein lengths. Here is just a quickly computation of the effective Lewis number from the formula I showed you before for propane, air, and as a function of the equivalence ratio. Now remember that the theory is built on what we referred yesterday as a dilute mixture. In other words, we have the fuel and oxide in small quantity relative to another. So when you compute the diffusivity, you have to be consistent with that definition. And therefore, when you compute the Lewis number of the fuel for lean condition, you have to compute it based on this understanding that it is the deficient component relative to nitrogen, okay? And so this is that limiting value. At the other end, the limiting value of the oxidizer is this one, 0.89. And so when you choose these two and you go back to this formula, you know this, so you compute the Lewis number, the effective one, for any phi that you want, okay? And so this is the graph that you see. So for propane, for example, the lean mixture have a high or above 1 Lewis number, right? Lean mixture. But rich mixture have a relatively smaller or near 1 or even a little bit below 1 Lewis number. In contrast, the hydrogen has the opposite trend because the Lewis number of the fuel is very small, okay, in very dilute system. And the oxidizer, it's here. Now, this is different than that for multiple reasons because it's a different mixture. And so you have to compute it according to the mixture that you have. And so for a hydrogen air, this is, again, the Lewis number that we are computing. It's quite low for lean condition, and it's above unity for rich condition. And that, of course, has an effect on the Markstein lengths, which has a similar type of behavior for different fuels. You see the hydrogen can go from negative to positive. Methane also could be, methane can also be, propane goes the other way around, the blue curve, and some other alcohol and so on. This is scaled, the Markstein length here is scaled with respect to the diffusion length or the flame thickness, which is a natural way to scale it. Okay. Then if you are interested to allow for variation of the conductivity and diffusivity in temperature, then the constant that we had before are a little bit more complicated. There are some integral, but again, they are definite integral. You compute it once and for all for a given sigma. And the effective Lewis number in this case also may be more complicated if you want to allow for different reaction order. Then it's not just phi minus 1 as I showed before, but this coefficient here is some integral that depend on the reaction order, A and B, which is here N and M. They're here A and B, but this is a generic integral of this G. So anyway, you can evaluate it. Of course, they, for constant property, it cover the previous thing, and for obvious limits, you get the right thing. So, okay. The flame speed, flame stretch relation show that it can be sometimes positive, or the slope can be positive or negative, which depend on the Markstein lengths and therefore depend on the equivalence ratio. So for propane, you see because L was positive for lean condition and decreases towards rich condition, then when it's positive, it gives you a negative, when it's, wait, what did I say here? Phi, propane. Well, here it is. For a lean mixture, the effective Lewis number is bigger than 1, and so that's why you get a slope that decreases. But for rich mixture, the Lewis number is slightly less than 1, and so you get a slope that increases. Okay? And for hydrogen, you get the opposite trend for the same reason we discussed before. Here you see where you can have confusion if you do measurements or computation at different reference location. So I'm going to be, again, brief about this due to timing, but basically, if you choose the reference to be T star is a different isotherm. And this is done from DNS of spherically expanding flame. So same DNS that I mentioned before. So if you choose the reference to be very close to the cold temperature, you get a slope like this. Very close to the hot temperature, you get an opposite slope. So which one is correct? Well, that is true even if you do a global or a detailed chemistry. You get also differing slopes. Well, for it turned out that, as explained in this paper, that the correct reference location should be as close as possible to the burn temperature. And the reason is that, oops, and that gives you the correct picture because the Markstein number varied tremendously across the flame if you choose different reference location. This is the flame. You see the flame run from 1 to about 7, 8, the temperature, right? And so near the burn gas, it doesn't really, if your reference location is near the burn gas, then the error is relatively small, whereas here you can have large error in choosing that as a reference location. Okay. If we go and recalculate or revisit the spherically expanding flame that we discussed earlier, and we account for the effect of stretch, we get a propagation speed. It's no longer R dot equal to sigma SL, but it has also a coefficient here that we refer to as the burn Markstein length. Doesn't matter the origin, I will skip that, multiplied by the stretch rate, which is computed here. Now this is interesting because now it depends on the Markstein length, and so it has in it the equivalence ratio. And I showed you earlier this experimental result where I show you that there is a difference between lean and rich, where the blue line here is between the curves that decrease towards the asymptote, whereas the other one increase towards the asymptote. And in fact, the theory shows a similar trend as well. So that is a nice consequence of this result. And this is another experiment done in Aachen by Beekman. It was the group of Norbert Peters, but it's a hydrogen-air mixture where they took measurement and then they wanted to compare it to the asymptotic result, and you see that the comparison is quite well between the two, okay, for a variety of conditions. Again, here it's hydrogen, so it's the opposite trend that you saw before. So for rich condition, you increase towards the asymptote. For lean condition, you decelerate towards. There are a few comments about flame temperature, but I will skip those. You can read them. The point here is that the point there was, I mean, in those flame temperatures that, for example, the numerical solution of a spherical flame show that there is a minor or very small change in flame temperature as the flame expands. So there is a weak dependence on stretch, because as the flame expands, the stretch rate, which is proportional to the curvature, decreases, okay? So the idea is that when it's very large, the stretch rate goes almost to 0, and you should tend towards the laminar flame speed and so on. What those notes show, and you will see them if you are interested, that there is a small variation in temperature related to stretch, and that the theory explains those exactly as the numerical show. So if you're interested in that, it's there. Okay, now the mathematical problem in the hydrodynamic model is essentially complicated, but it involved Navier-Stokes equation, density field dictated by this. I'm sorry that now F became psi, so psi is the surface, the flame surface. It just changed name over the time. And then we have the Rankine-Hungonian relation across the flame, and we are neglecting the extra small correction. And the flame speed relation, the more general flame speed relation, including flame stretch. So this problem have to be solved numerically, essentially. And there are effectively two parameters that you have in the model. One of them is the Markstein length divided by the length scale L, which I will refer to as the Markstein number. It's not the Marsden number that I defined earlier, which is relative to the flame thickness. So the difference is that L over L is L over LF, LF over L. This is the more conventional Marsden length, and this is effectively the flame thickness, okay? So it's convenient to define it this way because instead of specifying two parameters, I specify one. But eventually, if you want to relate it to experiment, you have to incorporate those two. So, and the other parameter is essentially the sigma, which is due to heat release or expansion ratio. So I'm going to show you a few examples where this was worked out numerically. By the way, this is known mathematically as a free boundary problem. It's not a typical boundary value problem because there's not only two boundaries, there's also a boundary in the middle which is free, it moves, and it's unknown. So it's a much more complicated to solve numerically. And the way it was done essentially is by using what is referred to as a level set approximation combined with a Navier-Stokes solver. So, oh, this is just, I didn't have to go here, it's in my slide, essentially to show you that there is a difference in the numbers when you refer it to correctly or not, I mean not correct, conventionally or not, and anyway. So here is the Bunsen flame, okay, a uniform flow coming out, and you see the model or the computation describe the flame surface, which has the correct angle that we can compute based on theta, but also it curved the flame correctly at the tip, which we didn't have in the simple theory. And here is the solution if you have a parabolic flow. And here is now you can see the unburned gas motion more clearly. This is the steady propagation of cusp-like flame that propagate into a quiescent mixture. The speed that it propagated, you see about 0.115, so it's significantly larger than the laminar flame speed. How do we get those? We're going to talk later on. They are a result of an instability, but I will discuss that later. Here I wanted to show you is just that we can compute them and we can obtain the streamline correctly. Note that the unburned gas streamline get deflected by the flame as we expected, and so it gives you the picture, as well as the velocity is about, sigma here is 4, so the velocity is about 4. Remember the sigma -1 or sigma was the jump in the velocity normal to the flame. Anyway, just to convince you that this is not just related to nothing, so here is the example I showed you before. I want to emphasize that the simplicity of this, even though the numerical methodology is not trivial to solve this free boundary problem, but you have only two parameters to specify. So if you provide a certain mixture, let's say propane air phi equal to 0.8, so we know what is the diffusion length scale, we know what sigma is for this condition, we know the activation energy parameter, or at least we find that in the literature, the one that fit a one-step model. So we can calculate the effective Lewis number from the formula before and the Marsden length, and so we have both sigma and the Marsden number. And this is the computation, this is the result. The conditions here are a little different than the previous example. Note that sigma is 7, so the propagation speed is not 1.15, it's 0.122 something, okay? It's as you expect. And here is a numerical simulation, DNS, of the same propane air, same condition. There is, of course, some differences near the flame, as you would expect, but generally speaking, the flow is very, very similar, okay? So, and the propagation speed is quite close. I mean, you don't expect it to be identical, but it's close. Oh, and that's the end. Wow, we finished earlier today. I don't know if earlier, but earlier than I thought. So thank you very much. I'll see you tomorrow.